Welcome to this training session on lithium-ion battery manufacturing. In this course, we will walk through the complete journey of how lithium-ion batteries are made, from the very beginning of raw material preparation, all the way to the final assembly and quality testing. Our goal is to help you understand each step of the process, so you can connect your daily work in the factory to the bigger picture of battery production. Let's begin our journey from the front to the end of lithium-ion battery manufacturing. We have now reached the final section of this training, the extra collection of process overview diagrams. In this section, we will examine various diagrams from different sources that illustrate the lithium-ion battery manufacturing process. While each diagram may look slightly different, they all represent the same core sequence of steps, with only minor variations in detail. By reviewing these different perspectives, we can enhance our overall understanding of the manufacturing flow and appreciate how each stage connects within the broader context of battery production. This block diagram provides a simplified overview of the lithium-ion battery cell manufacturing process, extracted from an MDPI study on benchmarking energy usage. As we can see, the process is divided into three major stages. First, electrode manufacturing, which includes mixing, coating, drying, calendaring, and slitting. Next, cell assembly, where stacking or winding is followed by packaging, welding, electrolyte filling, and sealing, typically performed in a dry room environment. Finally, cell finishing, which encompasses formation, aging, quality control, and sorting, before cells proceed to the next stage. This diagram does not extend beyond cell manufacturing to modules or packs, but it effectively captures the essential flow from raw materials to finished cells. This diagram, taken from the CIRP Annals on the water-based manufacturing of lithium-ion batteries, illustrates the process flow in a clear, step-by-step manner. On the left, we see the anode production steps, starting from mixing, coating, drying, calendaring, and notching. On the right, the same sequence is followed for the cathode. Both electrodes are then brought together with a separator in the central flow. From there, the process continues with stacking, welding, electrolyte filling and wetting, sealing, and precharging. Finally, the cells go through degassing, followed by final sealing and trimming. What makes this figure unique is that it highlights how the two electrode production streams merge into the shared cell assembly process. This image illustrates the manufacturing process of lithium-ion batteries, which can be broadly categorized into three main stages. Electrode manufacturing. This initial stage involves preparing the anode and cathode electrodes, including steps such as mixing materials, coating them onto foils, pressing, slitting, and notching. Cell assembly. In this stage, the prepared electrodes are assembled into a complete cell, which includes processes such as lamination, folding, welding, AL forming, electrolyte filling, and sealing. Formation and finishing. The final stage involves the initial charging and discharging cycles, formation/aging, sorting, recharging, and finally packing the finished battery cells. This diagram, taken from life cycle assessment considerations for batteries and battery materials, illustrates the major life cycle stages of both vehicle and stationary batteries. The process begins with the extraction and processing of raw materials, followed by the manufacturing of components and cells. Cells are then assembled into modules, which are in turn assembled into packs, and these packs are integrated into vehicles. After the vehicle use phase, batteries may enter a second life, as stationary storage systems. Eventually, at the end of life, they undergo recycling through pyrometallurgical or hydrometallurgical processes, or in some cases, disposal through landfill or incineration. Importantly, the cycle also includes recovery of materials and components for reuse, closing the loop for a more sustainable battery supply chain. This diagram, titled Lithium-ion Battery Production Process Flow Diagram, is adapted from Advanced Energy Materials, 2021. It shows the full production chain, starting with the manufacturing of electrode active materials, where raw materials such as lithium, nickel, manganese, and graphite are processed. Next is electrode manufacturing, which involves mixing, coating, drying, and calendaring, during which most solvents are recovered. However, some emissions remain. The process then moves into cell assembly, which must be performed in a dry room. Here, electrodes are wound or stacked, packaged, and filled with electrolyte. After that, in the cell finishing stage, cells undergo formation, aging, and testing before they are classified as finished cells. Finally, modules and packs are assembled using plastics, metals, and electronic components, producing the finished battery systems. This flowchart not only highlights each production step, but also identifies key inputs, such as electricity and solvents, as well as notable outputs, including waste streams and recovered materials. This diagram illustrates the cell assembly and finishing process for lithium-ion batteries. It begins with the preparation of anode, cathode, and separator, followed by two major assembly methods: stacking for prismatic cells and winding for cylindrical cells. In both cases, electrodes are connected, inserted into casings, and subassembled with terminals, vents, and safety devices. Next, the cells undergo sealing or welding and are then transferred to the dry room environment. Here, vacuum drying is followed by electrolyte filling, sealing, and labeling for identification. The process continues with formation cycling, where controlled charge-discharge cycles build the solid electrolyte interface (SEI). Afterward, the cells undergo aging, acceptance testing, and final packaging and shipping. Overall, this flow illustrates how multiple safety, precision, and quality steps ensure the reliable production of lithium-ion batteries. This slide presents a facility-level view of the lithium-ion battery manufacturing process, provided by Cognex. The diagram shows how different sections of a production floor are dedicated to each major stage of battery manufacturing. We begin with electrode manufacturing, where advanced machine vision and AI solutions monitor electrode coding, gauging, and traceability to maintain high quality at high speed. Next, in the cell assembly area, inspection systems are applied to processes like sheet stacking, tab welding, and seam inspection, helping to reduce rework and ensure strong functional quality. The cell finishing section emphasizes safety and performance. Here, high-speed defect detection, barcode-based traceability, and end-of-line inspections confirm that only compliant cells proceed forward. From there, the process moves into module assembly, where cells are integrated into modules. Automated inspections verify glue application, welding seams, and stacking accuracy, while traceability systems track each component. Finally, in the pack assembly stage, modules are combined into complete battery packs. Machine vision ensures correct assembly, identifies subtle defects, and maintains traceability of all critical pack-level components. Overall, this floor layout showcases how automation, AI, and vision systems are seamlessly integrated into each stage of the battery manufacturing workflow, enhancing quality, safety, and efficiency. Battery manufacturing automation and force sensors. This slide highlights the role of automation and precision force sensors in the battery manufacturing process. Each stage, from slurry preparation and mixing to coating, drying, calendaring, and electrode punching, relies on accurate force and torque measurements to ensure quality and consistency. Sensors also monitor key processes, including electrode stacking, tab welding, and pouch cell mechanical testing. By integrating these automated measurements, manufacturers can achieve higher process control, reduce defects, and improve overall efficiency in large-scale battery production. The diagram outlines the manufacturing process of lithium-ion batteries, which involves several key stages. Electrode preparation is the initial phase, where raw materials are mixed to create a slurry, coated onto foils, and then pressed and dried to form the coated electrodes. Cell assembly. The prepared electrodes undergo slitting and notching, followed by stacking or winding with separators, and then welding and assembly to form the basic cell structure. Cell finishing. The assembled cells are sealed, undergo further drying, and then filled with electrolyte, followed by impregnation, pre-charging, and degassing to optimize performance and lifespan. Final processing. The cells are then subjected to final pressing and folding steps before packaging, completing the battery manufacturing process. In this slide, we take a closer look at the wet electrode manufacturing process for lithium-ion batteries, focusing on the first sequence of steps. The process begins with mixing, where raw active materials, binders, and solvents are combined in vacuum mixers to produce a uniform slurry. Next comes coating, where the slurry is applied to current collector foils using precision coating machines. The coated electrodes are then sent into dryers to remove solvent, followed by compressing or calendering, where a calendering or pressing machine ensures consistent thickness and density. After this, the electrodes undergo slitting, where slitting machines cut them into precise widths suitable for stacking or winding. Finally, drying or vacuum ovens are used to remove residual solvents and moisture, ensuring the electrodes are stable before cell assembly. Each of these stages requires specialized equipment: vacuum mixers, coating machines, dryers, calendering presses, slitting machines, and vacuum ovens. Together, they form the backbone of high-quality electrode preparation, directly impacting the performance and safety of the final battery cell. This stage focuses on cell assembly, bringing electrodes together to form functional cells. The key steps involve stacking or winding the electrode layers, followed by packaging and sealing them. Welding is used to securely connect the tabs, followed by electrolyte filling under dry room conditions. The equipment involved includes stacking and winding machines, vacuum sealers, tab welding machines, and precision filling systems. All of these are integrated into a cell assembly line to ensure consistency and efficiency. This step is critical because it transforms prepared electrodes into an actual energy-storing cell. This slide compares various perspectives on the cell assembly process. The first diagram shows the general sequence of stacking, packaging, welding, and filling. The second highlights an automated cylindrical cell line with each machine step, from electrode preparation to testing and glove box handling. The third provides an internal look at a cylindrical cell, showing how electrodes, a separator, and safety features are arranged inside the can. Together, these visuals help us understand both the process flow and the equipment involved. This slide highlights the final stage of lithium-ion cell production, which includes formation, aging, and end-of-line testing. Cells first undergo formation, during which controlled charge-discharge cycles stabilize their electrochemical performance. They are then placed in aging cabinets to ensure long-term reliability. Finally, end-of-line testing equipment checks cell quality before shipment. These steps are essential to guarantee the safety, performance, and consistency of the finished cells. This slide compares the two primary approaches to electrode fabrication: wet coating and dry coating. In the wet coating process, a slurry is mixed, coated onto a current collector, dried, calendared for density control, slid into strips, and then vacuum dried. Solvent recovery is also required to handle emissions. The dry coating method eliminates the use of slurry and solvent. Instead, active materials are dry mixed, fabricated into a film, calendared, laminated, and slit. While wet coating is the industry standard, dry coating is being developed as a more sustainable and cost-efficient alternative. This slide presents the final products of the battery manufacturing process: cells, modules, and packs. First, lithium-ion battery cells come in three major formats: cylindrical, prismatic, and pouch types. Multiple cells are combined into a module, and several modules are then integrated into a pack. As shown in the images at the pack level, the system includes not only the cells and modules but also critical components such as the cooling system, battery management system, BMS, and protective housing, making it a fully functional energy storage unit ready for installation in electric vehicles. In short, this slide visually summarizes what the entire process ultimately produces: the complete form of the battery system. This concludes the extra section on lithium-ion battery manufacturing. We have now reached the end of this lecture, front to end of Li-ion battery manufacturing. Throughout the class, we explored the entire process from electrode production and cell assembly to cell finishing, module and pack integration. This has been a complete journey through the fundamentals and key technologies of lithium-ion battery manufacturing. Congratulations on completing the course. I hope this knowledge will strengthen your technical expertise and confidence in the fast-growing battery and EV industry. Thank you.